Hi everyone, this is Victor, and I'm happy to be here speaking about Akerbeltz, the first instance of robot ransomware for or targeting, better said, industrial collaborative robots. This is framed as part of the ERRoSS forum 2020, so I hope you enjoyed, and also take a look at the rest of the talks, which I'm sure will be awesome. So in this speech, I'll essentially treat Akerbeltz. Before that, I will shortly introduce our offensive approach and our offensive research, and then I'll leave the details of Akerbeltz in the paper, giving you a sneak peek, so feel free to extend your know-how by going to the paper and reading it directly. So first, Alias Robotics is the organization that's sponsoring me being here and having the chance to give you this speech today. Alias is a robot cybersecurity firm which essentially serves customers around the world with both services and products, trying to essentially make robots more secure. Alias has been built on top of about a decade of experience building robots and serving robotic solutions. Essentially their main product is an antivirus for robots that gets installed directly into the robot and protects it from the inside. As pointed out, Alias builds its solutions on top of about a decade of experience across different companies, building different robotic products and serving many customers and with different robotic solutions, which brings all together a pretty interesting set of skills which we have put together, including roboticists, computer scientists, cybersecurity engineers, safety engineers, all together into, again, serving our customers. So again, that's our journey. And what gets us real concerned and motivates our work every day is the fact that robots are really not secure. And they aren't secure in industry, in manufacturing. They aren't either in our roads. They're really not. And unfortunately, neither in our hospitals. And this is something we're trying to fight very actively. To do so, we're putting together a series of case studies. And we've been doing this for about a year, since we are, for the last year, we've been more active and public about our research. So if you're interested in what you're hearing right now and wish to learn more, I encourage you to go to aliasrobotics.com, our website, and check out some of the case studies we've been publishing for a while already, while cooperating with some of the top vendors, including KUKA, ABB, and some others. So to kick off a bit more of the core of the presentation, I wanted to start by giving you an intuition of what's the real status of cybersecurity in robotics for robots that are used in industry. You've got over here in both of the videos an industrial mobile robot from a company called MIR, which actually stands for Mobile Industrial Robots. This robot particularly is MIR, the MIR 100, and is one of the most popular robots that's used for automation in industry, but also for other tasks, such as, for example, fighting against the COVID-19. You might have seen this base, because it's just a base, used for disinfection tasks across different vendors. There are many vendors using this for the same thing. So reasonably popular, we can just say that, and unfortunately extremely vulnerable. In a past exercise, we discovered more than 100 vulnerabilities within this robot, many of which allow to take remote control of the robot and operate it at discretion of the attacker. Particularly here, we bring you two examples. The first one on the left essentially shows you how we disable the safety mechanisms. It has a SIG PLC, so we disable it remotely, and we can literally prevent it to stop when objects and obstacles are detected, and you can see it crashing real nice. The second video we bring to you is actually video that shows a bit more of a complex POC, proof of concept attack, which essentially, in this case, an exploit is executed which allows us to exfiltrate the map that's being generated dynamically by the robot. So you can see it here navigating through our offices, and you can see how real time we're just extracting the map that's being generated, and we can later on exfiltrate it, fetch particular images, and with this essentially plan an attack or explore or essentially just acquire additional information we shouldn't have access to it. And again, this can be done by exploiting numerous vulnerabilities, all of which are actually totally unpatched, will not be patched, and unfortunately our conversations with the vendor are not looking very optimistic because these robots are mostly not under control. The manufacturer does not care about security, does not have access to the robots, and the system integrators in many cases, they just simply don't have the means, or it's none of their business, leaving it for the final user, which typically just wants to use a robot. So that's what motivates this title, which is don't trust, don't use vulnerable robots. This is a very, very, very common theme in robotics currently, and we hope to make a change on this with our research, with talks like this one. So our approach to ensuring security in robotics is A, offensive, and B, defensive. I will not be speaking today about our defensive approach. If you're interested in this, I encourage you to go to our website and check what's called the Robot Immune System, or RIS for short. And if you have any questions, feel free to reach out and ask. I'll be speaking about our offensive approach to robot cybersecurity, and essentially what motivates this is the fact that we're seeing how robots are highly complex systems of systems, in fact. That's a good definition for a robot, to be honest. A system of systems, and systems where system integration is a huge part of the work of the overall process. So given this overall effort required to make it work, to make it useful for a real application, it's inevitable that somehow someone in the pipeline is going to either make a mistake or simply just use a component, a software component, for example, that's either not updated or simply has vulnerabilities that either haven't been patched, haven't been encountered yet. So the possibilities of covering all of the holes starts being, let's say, very difficult, especially because once again robots are made out of huge amount of parts, both software and hardware. So our approach to try to help our customers secure them is by essentially acting like the bad guys, dedicating a number of qualified engineering hours and giving them an insight of how much time would it take a professional, qualified and trained attacker in robotics to enter, to find holes, and to eventually exploit and leverage those holes to make something useful out of it. So this is what essentially motivates this offensive approach, this way to provide defense by essentially acting offensively. The attacker model we use when exercising this offensive approach follows from past work. We haven't really reinvented the wheel. In this case, we're reusing as much as we can from the great cybersecurity community. And in this case, this is the pipeline we follow, going from an initial reconnaissance phase down to a control phase, which is especially relevant in robotics. So from the starting till the end, you can see how we weaponize ourselves. We find a number of flaws, either testing the code, testing the system, or social engineering when we can, when the scope allows for it. We then proceed with a cyber-intrusion. We build exploits that essentially exploit one of these detected flaws. And from that point on, we start with privilege escalation, and then lateral movement. As I pointed out, robots are systems of systems, which means that entering the main computer or entering one of the subsystems of the overall robot does not necessarily mean you gain total control of the robot. Maybe you just entered the main computational unit, but that one actually cannot exercise control over a subunit which requires certain privileges. Though this is not the common case, but you might have been able to, for example, enter or penetrate into one of the actuators, which just gives you limited capabilities. So again, lateral movement is relevant. As you can see, lateral movement is composed by pretty much the same first few steps. Eventually, once we've gained enough foothold into the system, we go down to the exfiltration of data, and finally control, which essentially means we build custom exploits, we build custom attacks that allow us to make something that makes sense with the robot, which is just not enough to put a flag. In robotics, typically we need to speak the robot's language and make sure that we get the behavior we want to. Before diving further, I put together a number of definitions here for you guys. I'm not gonna go through each one of them, but I think that coming from a robotics background, it might be interesting for you to revisit exactly these definitions, especially because there's lots of contradictory thoughts about this in cybersecurity, in the cybersecurity community. So we don't claim these are the not even the correct ones. These are the ones we use ourselves, and particularly we are pretty picky about the difference between a bug and a vulnerability, in the sense that for us a vulnerability needs to be exploitable, it needs to be somehow reproducible. Whereas in security, many people consider the so-called theoretical vulnerabilities. We try to get as far as we can from that, especially in robotics, where reproduction is a pretty relevant and tough sometimes matter. Again, as I pointed out, our group has been working real hard on robot cybersecurity. We created back around, I think a year ago, something called a robot vulnerability database, which we have been populating with bugs and vulnerabilities over the past year, collecting currently, publicly speaking, more than 200 vulnerabilities and more than 1,000 bugs cataloged across different robot components and robots. Thank you so much to the organizations that have been supporting us, both private and public ones. And if you are interested in this, I encourage you to go over here and learn more about actual vulnerabilities for robots. What's more interesting that we've been putting together for the last few months is that beyond this public robot vulnerability database, we've been building a private version in cooperation with our clients and in cooperation with private funded projects. And I can tell you we are already about an order of magnitude above any of the numbers you can see on the public one. So if you are interested in either accessing the data or cooperating with us while doing research, feel free to reach out, and we may possibly give you additional data that's not currently publicly available. Of course, we act this way because of the sensitivity of some of these bits sometimes. So we would definitely be very careful in terms of what we open and what we don't. But nevertheless, this is how we are trying to contribute and lead somehow the security research in robotics. Real quick, as you can see in this plot, the current reaction of manufacturers is sometimes a bit disappointed. This is the case of Universal Robots, one of the leading collaborative robot companies, originally based in or headquartered in Europe, born essentially in Denmark, but then acquired later on by Teradyne, together with other companies. Actually, they're building a group of I would say insecure companies, or at least they don't responsively react to security research so far, and as far as I know. But an interesting thing over here is that you are, as of now, has actually passed over the 3-year range of not answering to security flaws. They just don't patch anything. And this means that, to some extent, all of the users that are using ERRoSS are totally exposed to these flaws. And I must highlight that our research wasn't the first one. There was prior research 2 years ago which highlighted similar matters. They didn't go as far as we went, but certainly found some interesting aspects that were never patched. So after many iterations, working with the manufacturer, seeing no reaction and getting real frustrated, we decided to demonstrate the vulnerability of these robots by building the first instance of ransomware targeting this particular robot, the robots from Universal Robots. And that's how we essentially built Akerbeltz. So Akerbeltz and more particularly ransomware in a nutshell, is essentially malicious software that either locks a computer. This is the, let's say, the computer-oriented definition, and prevents from accessing the data using encryption or both until the subject has paid a ransom. So in ransomware, the important matter is the fact that the computer or the robot in this case is locked or encrypted, certain parts of it, the intellectual property, for example. And in order to unlock or get again access to this data, you need to pay a ransom, which actually may unlock or may not unlock the robot at the end. And as you can probably read publicly, lots of things happening over this. To give you a sense of intuition, there are two main groups of ransomware, though things are kind of like getting mixed together in the more contemporary versions of ransomware we're seeing out there. The first big group is what's called crypto ransomware, which encrypts data and asks for a ransom to essentially exchange it for the decryption key. And the second group is the locker ransomware, which locks the system, prevents its use essentially, and then the ransom allows to re-enable its use, but there's no encryption. At least it was like that at the origin. This has developed actually for quite a few years. Ransomware is quite old. It was the first instance actually happened in 1989, which is a funny year because I was born that year. So quite old. I'm already quite old. So ransomware is quite old. And the first proof of concept was actually built and shown in a conference out of research action from an evolutionary biologist. So pretty creative biologist, I would say. The following 10 years or so, approximately, most of the instances of ransomware that were seen were crypto ransomware. So essentially ransomwares that were encrypting and asking for a ransom in exchange of the decryption key. Then there were about 6 years of locking ransomware. So crypto locker gets real popular. And sorry, there's a typo over there. Actually, it's not crypto locker. From 2007 to 2013, there is a locker ransomware getting popular. And then in August 2013, what happens is that crypto locker just shows up for the first time and then starts growing like hell. Even as of now, today, the most popular ransomware you may see out there is actually either crypto locker or variations of this. So you could probably just claim that this is the most popular instance of ransomware out there. Crypto locker combines both crypto ransomware and locker ransomware. So it locks the system and it encrypts sensitive parts of it so that you require the key to use it and to retrieve your data. And this was exactly the philosophy we used to build our POC to further demonstrate the vulnerability of this robot. So with that in mind, we built Akerbeltz. And Akerbeltz is a pretty simple, actually, version of ransomware targeted for this particular robot. If you're curious about the name, you've got over there some additional details. Essentially, it comes from mythology, from our culture here in the Basque Country. But I will not get into this out of time. And I will just point out that Akerbeltz does three things. First, it uses the identified vulnerabilities to intrude into the file system. Once it has intruded into the file system following the pipeline I showed before, actually, it moves laterally. So it does number two. It moves to other subsystems, including the teach pendant and some other safety subsystems. And then three, it takes control of the robot. In particular, control is exercised in this case, in this POC of malware, by encrypting sensitive parts of the file system and overall locking the functionality of the robot. Let me show you how this actually works. There we go. So you can see here POC, the public POC and video we showed actually about a year ago in Germany, face-to-face with the vendor actually, and we saw still no reaction, unfortunately, but we're still hoping that this happens. So you can see here the robot moving and working usefully without any issues. And now we inject a version of Akerbeltz through this attack vector. We used a physical attack vector, and what happens automatically is that it just gets triggered, it gets installed, It exploits the existing vulnerabilities, it moves laterally, it takes control of the subsystems, including the safety and the teach pendant, disables safety, gets printed this message, and then encrypts and logs the overall system. So as you can see, we just dump here a funny message asking for a donation in Bitcoin. Actually, I don't even think that there's Bitcoin over here. Yeah, we didn't even bother to put that. And by the way, I don't know whose wallet address is this one, but certainly not ours. So if you want to donate, don't do it here. just reach out, please. But jokes aside, we once again did this to try to shed some light into the current vulnerability of these robotic systems. This is one of the most popular robots used currently for industrial automation tasks. And similar attacks can be very, very easily, at least for qualified robotics engineers, deployed in other industrial robotic systems. In some cases, it's much, much easier than what we've shown over here. So we definitely encourage all of you interested in cybersecurity to be active, to try to find ways to influence the growing interest to secure robotic systems. If you don't know where to start, reach out. We're always happy to cooperate with talented researchers. And I think I've got a final slide which gives you an intuition of how much value we added to this vendor and how much you could add yourselves if you essentially get into this field and start contributing. So at the time we grabbed this robot, there were 5 public vulnerabilities, 5, which were not patched. And these ones actually remain as of today, as far as I know. After our exercise, which went on for, let's say, a few weeks, including several persons, actually, we found a total of more than 300 vulnerabilities for this robot. And we are still performing active research from time to time, revisiting our past work and finding even more and more. So I think the total count right now is significantly higher. So long story short, the current landscape of vulnerabilities in robotics is concerning. Most industrial robots need to revisit their security posture. We consider one of the most popular collaborative robots in industry and essentially executed penetration testing, which led us to a huge number of vulnerabilities which were not patched at all. Out of the reaction and essentially lack of acknowledgement from the manufacturer, we decided to build a POC demonstrating how ransomware was trivial to implement and to deploy, using either physical attack vectors, as you've seen in the video, or remote attack vectors, such as any connection, wired connection typically, that the robot may have. And that's pretty much it. Again, there are more details of our implementation within the paper. Feel free to read it. Feel free to reach out if you have questions. And other than that, thank you so much for listening. I hope you stay safe and secure as well, which is as important. Take care. Bye-bye.